And last time we mentioned that lithium aluminum hydride as a reagent can't take an ester or an acid chloride and stop at the aldehyde. Instead, you reduce all the way to the alcohol. And though we won't talk about these, what I'm going to write next specifically today, I want you to be aware of it. Your study guide takes you through it. You should know the mechanism for what I'm writing here, reduction of esters and acid chlorides to alcohols with lithium aluminum hydride. It turns out you can do this with just the carboxylic acid too. Your book mentions it. I don't know anybody that actually does this, so you might encounter this on, say, standardized exams in the future if you've got MCAT or DAT in your future. I want you to be aware of that. I'm not going to hold you responsible for this, the mechanism of reduction of the acid. I know some of you are going to worry about this and want me to say it again or at least put it in writing, so I want you to know this mechanism here for those. Don't worry about it for the acid. Lithium aluminum hydride also works for amides and can reduce, I'm abbreviating lithium aluminum hydride, can reduce the amide not down to an alcohol but actually to an amine. And the reason the reason the nitrogen stays there is that the nitrogen's a poorer leaving group than an oxygen. You don't need to know these mechanisms here, but I want you to be aware of them in case you encounter them in the future, okay? But I won't really say much more about these two reactions. All right, so what if you wanted to take an ester and stop at the aldehyde? There's a couple reagents your book presents. I'll talk briefly about both of them. Really, we only need one of them because as far as your text is concerned, you can use them interchangeably. But there are two strategies for stopping at the aldehyde. Okay, strategy number one is a less reactive form of lithium aluminum hydride. So you still use lithium, and you still use aluminum and an aluminum hydrogen bond, but instead of having three other aluminum hydrogen bonds, you have three oxygens. There's a negative formal charge on aluminum, and then you have T-butyl groups on all of those oxygens. And if you try to pronounce this name, it's like terrible. It makes you cry like that. Lithium tri-tert-butoxy aluminum hydride. It's terrible. And the reason that this can stop at the aldehyde is you have these electronegative oxygens attached to aluminum that are pulling electron density away from the aluminum hydrogen bond. Remember, this is a carrier of H-, and so if you do things that pull electron density away from that H-, it's going to be not as good of a hydride deliverer. And so it's observed that you can take either an acid chloride or an ester, and if you use this reagent with the name that is difficult to say, you can stop at the aldehyde. Usually after all of these reactions, there's a aqueous workup stage, so I'm going to write that explicitly there, but you can stop at the aldehyde. Okay, that's strategy one. You probably are going to need to memorize this reagent. I don't know what to do if you forget what this reagent is. However, knowing its structure should help you remember that it's less reactive than lithium aluminum hydride and that you can therefore stop at the aldehyde. Second, is a reagent called Diisopropyl, which stands for Diisopropyl aluminum hydride. This is a different kind of reagent because unlike the two previous ones, lithium aluminum hydride and then the horrible one whose name is difficult to pronounce, actually saying that is almost as bad as saying lithium tri-terbutoxy aluminum hydride, so whatever. This one's neutral. There is no negative formal charge on the aluminum. And your text doesn't really explain how this works, but it's pretty well understood. What happens is first, if you bring this into the presence of a carbonyl compound, let's say this methyl ester, the lone pairs on the carbonyl oxygen attack the empty p orbital that's on aluminum. Remember, aluminum, same column of the periodic table as boron. Aluminum bonded to three things would be sp2 hybridized with an unhybridized p orbital on that aluminum. That is the lowest unoccupied orbital of that molecule, and therefore the place where electrons will go if we have a nucleophile. And so once we do that, that converts what was previously neutral aluminum to now a more reactive hydride delivery reagent. And at this point, you can do an intramolecular reaction where aluminum delivers the hydride to the carbonyl carbon and the pi bond breaks. And then, let's see, I need a little bit of room for drawing this. And then what's left is, here's your new carbon-hydrogen bond. Here's the methoxy group that was from our ester. And then there's our carbonyl oxygen now bound to aluminum. So this is sort of, this is our tetrahedral intermediate, but it looks different because we don't see a negative charge on what used to be the carbonyl oxygen, because that carbonyl oxygen is bonded to aluminum. And it turns out that this tetrahedral intermediate, without the negative charge on it, is stable until aqueous workup. When you add water, water can compete with this oxygen for binding to the aluminum. And so in the presence of water, you can break the oxygen aluminum bond. And now when you have a full negative charge on that oxygen, you can kick off the ester carbonyl compound to get the aldehyde. So the reason that Diisopropyl works, I'm going to put, let's see, I'm going to show you what happens to the aluminum too. So you'd get sort of the aluminum hydroxide instead. The reason that Diisopropyl works is it pauses the tetrahedral intermediate. So we never, after we've added one equivalent of hydride, we never regenerate the carbonyl of the aldehyde until after the reaction's done and we've quenched the reagent. So it's kind of a cute little trick. And either of these methods you can use to take either esters or acid chlorides and stop at the aldehyde. Okay, questions so far? Yeah?
So just making sure I understand correctly, this is for like all the carboxylic acid derivatives.
So is this for all the carboxylic acid derivatives? Your text never uses Diisopropyl or the other reagent on these types of molecules, presumably because it doesn't work. So I'm not gonna ask you, oh, try to reduce this carboxylic acid using either of those reagents. I won't throw that at you. Okay, what else? Yeah.
What is it that makes the oxygen that flies off that carboxylic acid derivative?
Why here, you mean?
Yeah, that's
It's not, yeah, good question. It's not that it's a good leaving group. It's that if you compare, because it's not a particularly great leaving group, but relative to this negatively charged oxygen, it's okay. If you compare sort of stability of this molecule versus this molecule, both of them have negatively charged oxygen, so the equilibrium ought to be okay. And then the other thing that helps you is that you're in water at this point, so as soon as that negatively charged group comes off, we can protonate that and be done. Okay, good. What else? Okay, so that's going to finish reduction for us. Now we're going to talk about using carbanion-like nucleophiles, and the story is going to parallel exactly what we did with reduction. Okay, we're going to see that aldehydes and ketones give us addition products, and we're going to see that with carboxylic acids, we have acid derivatives, we have the opportunity for some additional complexity. So let's talk about carbon or carbanion-like nucleophiles. As you know, an sp3 hybridized carbon-hydrogen bond has a pKa of around 50, which basically means that the corresponding carbanion is really, really, really unstable, really, really reactive. And so, as with sort of hydride, we're going to need a carrier of the carbanion to deliver it as a nucleophile to our electrophiles. And the way we typically do this is that we bond the negatively charged carbon to a metal. And this process, or this kind of reagent where we bind a negatively charged carbon to a metal, that's called an organometallic reagent. And there are three types, there are many types of organometallic reagents. There are three that we will discuss in this class. One is the organolithium reagent. This would involve a covalent bond between carbon and lithium. We're going to imagine in our minds as though this were the carbanion and then lithium as the counter ion. That's actually not how it is. There's a fair amount of covalent character to that bond between carbon and lithium. Moreover, some of these organolithium reagents actually aggregate to form complexes. If you want to start to feel really uncomfortable about your life, we can start drawing strange things like this. And then we can start making even larger assemblies with other lithiums. Anyway, the story gets complicated, so be grateful that we're going to oversimplify it and think of the organolithium reagent like that, okay? There's another class of reagents that we'll talk about that do basically the same things as the organolithiums. I think your text presents them for historical reasons, and perhaps because when you take 353, you're actually going to do this Grignard reaction. The Grignard reagent also has a covalent bond between carbon and a metal, only in this case the metal is magnesium. Now you'll notice magnesium is in the second column of the periodic table. That means the ion of magnesium is magnesium 2+. So if you're balancing charge here, in order to be neutral, if we've only got one carbon group on the magnesium, we need a counter ion. In many cases, that's a halide, so commonly in your text we'll use bromide, okay? Now, there are a lot of ways to think about this reagent. You can think about there being a covalent bond between both magnesium and carbon and magnesium and bromine. If you want, it's simple to think of it as the carbanion plus the magnesium 2 plus ion plus Br minus. There is some evidence that sometimes instead of having a Br here, magnesium can be bonded to 2 alkyl groups. There is some possibility for aggregation, but we're going to think of things in this sort of simple picture. Also, the fun thing about doing a Grignard reaction is that the Grignard reagent is kind of Pepto-Bismol pink. So when you go do that in the 353 lab, color changes are always amusing. So there you go. Lastly, we're going to introduce a reagent called a cuprate. Cu is for copper. We're going to use a copper 2 plus, and it's going to be covalently bonded to 2 different alkyl groups. Let's see, I'm wrong because it's not copper 2 plus, is it? It's just copper plus. Now I'm embarrassed. Yeah, it's just copper plus. So the cuprate reagent looks like this. But again, we're going to think of it as though it is 2 of the carbanions, 1 copper plus, and 1 lithium plus. And it's more complicated than that, but that's sort of where we are. In terms of their reactivity, we're going to see that the organolithium reagent and the Grignard reagent are very similar to each other. They are strong nucleophiles. The cuprate is a strong nucleophile as well, but it's going to have slightly different reactivity. And we'll see that one reason for that is that copper is a different metal than lithium or magnesium. There's this whole thing that you probably didn't learn about in general chemistry. It's called hard-soft acid-base theory. It's something that we don't need to talk about in an introductory organic chemistry class, but the cuprate is a softer nucleophile than the organolithium reagents, and that's going to mean that it does some different things. That's a memorized detail. We're not going to talk about fundamental principles there. Okay, so how do we make these reagents? You can make them from alkyl halides. So as an example, if you take the corresponding ethyl halide and you add lithium metal, I'm going to use a little superscript 0 to indicate that's lithium at the 0 oxidation state. You get lithium metal, which you can get out of your lithium batteries if you want. It's probably a terrible use of your lithium battery, but if you wanted to, I guess you could. And that will, through a mechanism you're not responsible for, convert the alkyl halide into the organolithium reagent. It involves basically some electron transfer and some radical-like stuff that we don't need to worry about. Similarly, if you take the alkyl halide and you add magnesium metal, you can do the same thing. And you'll do this in 353. You'll take your alkyl halide, you'll dump the magnesium metal in it, and you'll reflux it, and you'll make the reagent. Yeah?
Is it important to remember, so the book talked about how you need 2 equivalents of lithium or magnesium.
Do you need 2 equivalents of lithium or magnesium? To balance things out, yes, but we're not going to worry about that. Yeah. Because, yeah, in the end, you do need 2 equivalents because you're going to make both the organolithium reagent and lithium bromide. Anyway, to make the cuprate, we actually make that from the organolithium reagent. So we take 2 of these, we add copper iodide, and that gets us to the organolithium reagent. I'm sorry, that gets us to the cuprate through a mechanism, again, that we're not going to worry about. Some of the synthesis problems in the text, though, are going to do really sort of cute things like oh, start with an alkyl halide that's 2 carbons and then do all these reactions, and you'll have to actually make the organolithium or cuprate or Grignard reagents to do the chemistry. Go ahead.
Why use cuprate if you already have the organolithium? What's the advantage of it in a reaction?
Great question. Why are we even doing this if we already have 2 useful things? Well, everybody's anxious to get their name on a reaction in organic chemistry, so discovering a new reagent and marketing it as useful can be somewhat lucrative. But beyond that, the cuprate actually does things differently. So this is a preview of something we're going to talk about in a little bit. This is an alpha-beta unsaturated carbonyl compound. It's a double bond conjugated with the ketone. Because of that conjugation, this molecule is not only reactive at the carbonyl carbon, but it's also reactive at the beta carbon. This has to do with the fact that when you have a conjugated system, you have an extended system of pi orbitals. You maybe learned about that in your chapter on conjugation. We're not going to make a big deal out of it here. But there are 2 reactive centers. And we're going to see that if you use an organolithium or a Grignard reagent, the reaction adds the nucleophile at the carbonyl carbon so that you end up with, after aqueous workup, you end up with the alcohol where you added your nucleophile here. But we're going to see that if you instead use the cuprate, after aqueous workup, you make a new bond between your R group and the beta carbon. And the ketone remains intact. So that's one place where cuprates are different from organolithiums and Grignard reagents. Okay? Yes?
What effect does the length of the alkyl chain have on the reagent? Is it always an ethyl group?
Is it always an ethyl group? No, you can do a number of things. Ethyl, propyl, butyl is fine. Basically any alkyl halide that you can make. Even aryl halides work well, so you can make a phenyllithium or phenyl Grignard reagent and do reactions that way too. There's one other, so we just as well talk about this now when trying to deal with why cuprates to begin with. So the idea is structural diversity. If you can take the same starting material, but with a different reagent, get 2 different structures, that gives you versatility to make lots of different things, okay? And notice how different these things are. This is still a carbonyl, this is still an alcohol. We have a new carbon-carbon bond here at a totally different part of the molecule. That's flexibility, that's diversity. And when you're in the pharmaceutical industry trying to invent new drugs, being able to make as many possibilities as you can and then test them is one of the key ways of identifying new medicines. A second difference has to do with how these reagents react with carboxylic acid derivatives. In particular, acid chlorides is sort of the only one we're going to worry about. With Grignard reagents or organolithium reagents, it turns out that, as you would expect, the mechanism of this reaction is similar to reduction. The carbon R group will leave with its electrons and attack the pi star of the carbonyl compound. That's going to give you the tetrahedral intermediate. And as before, the question will be, well, do we have a good leaving group? And we do, and so chloride leaves. But as we saw in the section on
adding hydride to carbonyl compounds. We've got a new carbonyl compound that is reactive at the carbonyl carbon. And just like lithium aluminum hydride, organolithium reagents or Grignard reagents are not good at stopping at the ketone. They are reactive enough that you end up adding again. And at this point, there's no good leaving groups on this tetrahedral intermediate. So there you're stuck until the aqueous workup step, wherein you protonate the oxygen and you get an alcohol. But it's not only an alcohol, it's a tertiary alcohol where 2 of the 3 things on that carbon are the same. So this kind of thing is exactly analogous to what we did, say, with an acid chloride or an ester when we use lithium aluminum hydride. You can't stop after one equivalent. You have to go all the way. Does that make sense? You see the analogy? In contrast, the cuprate, because of its different reactivity, and there's no fundamental reason here that I can cite for you, you're going to have to just memorize it. In contrast, you take the cuprate, you take the acid chloride reagent and you react it with the cuprate, and you can get away with only one equivalent of R minus adding, such that you get out of this reaction the ketone. You can stop after this first addition step. And the pattern here, instead of the product being a tertiary alcohol with 2 of the same R group, this is now an asymmetric, well, maybe that's not, I don't know. This is a non-symmetric ketone. That is, it's a ketone where the one R group is different from the other R group. So that's why cuprates. It allows you to take the same starting material and get different products. Yeah? Do both of the R groups on the copper have to be the same? Yes, I think, if you don't want mixtures of products. Yeah. Good. What else? Go ahead. What's the point of doing the aqueous workup step in the cuprate? Excellent. You've noticed that the product doesn't have anything to be protonated, so why bother? It's most likely to quench the remaining reagent and just make it convenient to isolate the product. In general, I'm going to be sort of flexible as to whether or not we show the aqueous workup step. It's often a thing for all reactions, and so it's just sort of assumed when people write out synthetic schemes, but I'm trying to be as clear as I can here. Okay, other questions? Yeah?
So for example, on a test, you wouldn't have one option where it's like the O minus and another has the OH on it without saying that there's aqueous workup.
Oh, right. So yes. Good. You're trying to expose my nefarious schemes, right? On an exam, what I have, this is the option and this is the option. And there would be some trick as to whether you're supposed to intuit that water was present or not. No, I got bigger fish to fry than that. So, all right, good. What else? All right. So, what have we seen? I mean, we've sort of taken, done an aside here because we've talked about cuprate reactivity versus organolithium and Grignard reactivity. But all of this is just variations on the same theme, right? So let's review with some specific examples. Instead of just generic R groups. And let's have you predict the products. Here is an ester. Here is a reagent. This is called N-butyl lithium. Sometimes people call this Bewley, but that's only the most annoying organic chemists that call it Bewley. When you use, because we know that organolithium reagents or Grignards, when they react with esters or acid chlorides, can't stop at the ketone, we're going to assume that there's 2 equivalents of the organolithium reagent. So you predict the products here. Ooh, should I make it like a test question? All right, you work on predicting the products. I will blank the projector screen, and you won't be able to see what I'm writing, and then we can select our answer. You ready? Okay. Okay. You have a guess at least that you sort of written down? Okay. Ta-da, there's the screen. And you get to choose the answer. And sometimes there'll be way more than, you guys were thinking multiple choice, like choose between 2 or maybe choose between 4. This isn't elementary school anymore, folks. You're going to have to choose between A and like J because the testing center makes me stop at J, all right? So, what do you got? D? Okay, good. It's D. Why isn't it A? Because you can't stop, right? That A is an intermediate. A is an intermediate, right? Because we get, and on questions like this, you don't have to draw the mechanism, but sometimes it can be helpful to know the mechanism to guide your thinking. But yeah, we kick off the methoxy group to give us A, but then another equivalent of the organolithium reagent attacks. And then after protonation, we get D. Does that make sense? Yes?
So addition of cuprate would stop the intermediate?
Yes, so if you want to change the question and make A the correct answer, yeah, if you use the same starting material, what about that? Actually, your text never shows you cuprates reacting with esters, I think because it doesn't work. But I'm not going to push you on that point specifically, but if you took the corresponding acid chloride and the same cuprate, yes, you could stop at option A. Yeah. Okay, so that's a way of testing your understanding of this kind of thing and how to think through these reactions. Yes?
Well, we need to know the way cuprate attacks the reagents similar to the way we learned it for organolithium, or do we just need to know that it just stops after 1?
Okay, so you do need to memorize that it stops after 1 addition. In terms of the mechanism, though, you're going to draw it exactly the same way.
You're going to take the electrons in the bond between carbon and copper. You're going to have carbon leave with its electrons, but that's a direct handoff to the carbonyl carbon to give you the tetrahedral intermediate, which looks like this. And then lone pair electrons kick down, kick off the chlorine, and that gets you to your product. Yeah, so that mechanism is just the same. The players are different, but the mechanism is the same. Okay, questions? Now let's actually ask another question in a similar way. How about this? I have, making up stuff is hard. Okay, fine. This is challenging. We'll jump straight ahead to the most challenging one. What if you have a tertiary alcohol where you have 3 different things? Oops. 3 different colors for 3 different things attached to that carbon. Or rather, what if, suppose, what's the difference between these 2 situations? Oh, darn. Can you think of a way that I might make this molecule? And what we're doing here is retrosynthetic analysis. We're asking, what reaction do I know that gives as a product a tertiary alcohol with 2 of the same things? And go ahead.
If you had the phenol attached to carboxylic acid and reacted it with the cyclohexene attached to the lithium.
Okay, so let's use as our nucleophile cyclohexyl lithium. Over here, this actually gives us a chance to bring up a good point. What should this be? If we have a proton there, okay, so yeah, if we have a proton there, actually, and this is something I didn't mention that I should, all of these reagents are strongly basic, as you would expect negatively charged carbons to be. So you have to avoid solvents that have acidic protons, and you would avoid carboxylic acids because the first and simplest thing to happen is you deprotonate the carboxylic acid and then you're done. So we're going to use solvents that don't have acidic protons. But in any case, yeah, you were mentioning I could have had, say, the ester, right? And then the ester would react with 2 equivalents of that organolithium reagent. We would have an intermediate ketone which would go on to react again, and there we go. Okay. Well, oh, did I just erase things? There we go. All right. What if instead I wanted this? What if I wanted a tertiary alcohol, but I didn't want 2 of the same thing? I wanted different things. Go ahead.
Could you use the cuprate first so it would reduce at once, and then you could use one with lithium?
Ah, okay. That's very interesting. Let's think about that. So we're going to start with the same starting material. And then you're saying, let's just use one as the cuprate. I don't know which. Let's use benzene since benzene's easy to abbreviate. Oh, wait. We would need to use the cyclohexyl, I guess. And that would give us, like you said, the first ketone. And then, because cuprates can stop, then I could use the organolithium or the Grignard reagent followed by aqueous workup to get me to that product. Yeah. Okay. So different reagents, different tools, different reactivities, same basic mechanism allows you to get to different types of products. So this is, you need to be able to think strategically here. One, I guess, word of advice on trying to keep up with all of these reactions, and that is that understanding the mechanism, as we've talked about, allows you to see parallels. These are not different reactions. They are different manifestations of the same basic reactivity. Nucleophile attacks a carbonyl carbon where the pi star is. But nothing is going to save you from forgetting key details like cuprates stop at the ketone or dibol stops at the aldehyde. So I have recommended in the past, and I don't know how useful it's been, that if you're struggling to remember details, imagine to yourself 3 sorts of quizzes that you give yourself. One where you have to take a starting material and a reagent and you predict the product. By the way, here it's a tertiary alcohol. Or another where you take the starting material and the product and you have to figure out what the reagent is. And then another in which you're given the product and a reagent, and you have to say what the starting material would have been. This allows you to think through reactions forwards and backwards and in the middle, and that will help you not only on predict products questions, but on synthesis questions to be able to think strategically. So if that's useful to you, go ahead. If you like flashcards, go ahead. But that's the kind of familiarity you need to have with these reactions. All right, questions? Really? Or are you just overwhelmed? Nobody's seriously going to take the chance to try to stop me from teaching new stuff in the last 10 minutes? Yes?
Scroll up just a little bit so I can see that.
Yeah.
Does it matter if we at the standard group or we have done the other way around?
Does it matter that we did it this way, that the cuprate had the cyclohexyl ring and the ketone had the phenyl group, or could we done it? No, we could have put any one of these 3 at any of these positions and it would have worked. Yeah, go ahead.
Would that change the stereochemistry depending on where it goes?
Would that change the stereochemistry depending on where it goes? No, notice that I didn't show you dashes or wedges, so I communicated both enantiomers here. Just like the reduction reactions, these reactions of the organolithium, Grignard, and cuprate reactions occur from above or below, and so you get both stereoisomers. Yeah?
Similar to that question, if you had an organolithium reagent, could it be attached to the phenyl group, or would that not work because the carbon would be sp2?
No, you can use, the reaction you're proposing works just fine. So I don't know. I mean, you can, even though it's sp2 hybridized, you can totally make the phenyllithium reagent and get the 2 benzene rings in your product. Yeah. Uh-huh. What happens with an amide? Is it similar to the carboxylic acid? Amides, I'm not sure. Your text actually doesn't say, so I'm not going to make a big deal out of it. Amides are not particularly reactive because because that nitrogen's a good electron donor. These lone pairs donate into the carbonyl carbon, and so it's not that electron poor. This is a potentially acidic proton that an organolithium reagent could remove, so it doesn't work particularly well, and nobody does that particular reaction. Okay, did I see another hand? Yeah.
Is it the fact that the carbonyl is triple planar that allows us to ignore the steric hindrance of these large nucleophiles?
Oh, sure. So the question is, some of these nucleophiles are pretty large.
how can they still add? And yeah, it's the fact that the carbonyl compound is planar, so you've got all the room in the world to do the attacking. All right. Yeah.
Can we use these nucleophiles in other reactions we learned in 351?
Yeah, can you use these nucleophiles in other reactions that you learned in 351? For sure. So a classic example of that would be, say, epoxide opening, right? You can totally open epoxides with Grignard reagents, and they're going to behave as strong nucleophiles. So if it's an asymmetric epoxide, you're going to open up at the less substituted carbon because of sterics. Yeah, that totally works. All right, so I mentioned the alpha-beta unsaturated carbonyl compounds, and I just want to show you a couple more, one or two more examples of that to make things totally clear. Here is another enone, or because enone is hard to say, I just call them alpha-beta unsaturated carbonyl compounds. That's more of a mouthful, but it's less vowel-y, I guess, than enone. Enone, I don't know. So if you have this alpha-beta unsaturated carbonyl compound and you were to add butyl lithium to it, that would add at the carbonyl carbon. The reason for that has to do with the fact, like I told you before, that organolithium reagents and Grignard reagents, Texas carbon. Let me back up and show you the product. The reason it adds to the carbonyl carbon has to do with what I told you before about organolithiums and Grignards being strong, hard nucleophiles, and that's an explanation that derives from some more OChem that we're not going to talk about. So this will be a memorized detail that you attack at the carbonyl carbon. By the way, this process is sometimes called 1,2 addition, because if this is carbon 1, 2, 3, and 4 of your alpha-beta unsaturated carbonyl compound, the things that get added in the reaction are added to positions 1 and 2. I don't ever call it 1,2 addition, but sometimes people do. In contrast, if you use the cuprate, you will instead add the nucleophile at the beta carbon. Here is the new bond that you make. 1, 2, 3, 4. So here's the new bond that you make. Sorry, and I'll just illustrate the alpha and the beta carbons. Now, how does that mechanism occur? Maybe one more minute, so we'll get started on it and probably need to review it next time. How does that mechanism occur? Well, as I told you, some of the LUMO is out on this beta carbon for reasons that you can accept on faith, or if you want to know more, you can come talk to me. So we can attack the LUMO here and make a new carbon-carbon bond. If we stop there, we'd have too many bonds to carbon, right? So we have to break this carbon-oxygen pi bond. At this stage, we can either put the electrons here on the alpha carbon, or we can move them here to form a carbon-carbon pi bond and then break the carbon-oxygen pi bond. So there's our new carbon-carbon bond, and then we make this intermediate. And then if we have electrons kick back down, we can protonate this intermediate on the alpha carbon to get our product. There's more to say about that, and I think we'll talk about it a little bit more next time. Yeah?
When we add the alkyl group to the beta carbon, do we create a stereocenter? Yes, and you'll get both varieties because you can attack from above or below. All right, thanks folks. Have a good weekend. See you Monday.